All right, let's run through another chemistry question. This one says ethylene diamine has an empirical formula of NH2CH2. Assume that 95 milligrams of ethylene diamine in the gas phase has a pressure of 235 millimeters of mercury in a 125 milliliter flask at 25 degrees Celsius. What is the molecular formula of ethylene diamine? All right, so an empirical formula is basically just broken down to the simplest ratios. So what we're trying to figure out is if the molecular formula for ethylene diamine is the same as the empirical formula. So is this the natural molecular structure for this particular molecule? So what we need to do to figure out if that's the case is to figure out the molar mass of this chemical. And then we'll figure out if the actual molar mass of the molecule matches that molar mass. So first let's calculate the molar mass of this empirical formula. We don't know if this is the actual molar mass of the actual molecule that's being worked with, but we'll be able to figure that out. So here we've got a nitrogen, we've got a carbon, and we've got 4 hydrogens because there's 2 hydrogens plus 2 hydrogens. Nitrogen is 14.007 grams per mole. Carbon is 12.00011 grams per mole. Hydrogen is 1.008 grams per mole. I'm going to multiply that by 4 because there are 4 hydrogens. So our molar mass for this empirical formula is about 30 grams per mole. Now we want to calculate the actual molar mass of this molecule. We can do that using PV equals nRT. So since we know we have 95 milligrams of this substance, we have the grams. If we divide by the number of moles of the substance, we'll get the molar mass because molar mass is grams per mole. So we're working with the ideal gas law, which is PV equals nRT. And again, we're looking for moles in this situation, so we can just solve this equation for moles. And that's going to look like we're just going to divide by RT so that we can get N by itself. So it's going to be N equals PV divided by RT. That's our rule that we're going to be using. So typically we want volume in liters and temperature in Kelvin. So let's make those changes quickly. 125 milliliters, there's 1,000 milliliters in a liter. So 0.125 liters is the same as 125 milliliters. And then to change from Celsius to Kelvin, you just add 273. So this is 298 Kelvin. Now we can just plug these numbers into our equation. So N is going to equal the pressure, which we have at 235, times the volume, which we just wrote as 0.125, divided by R times T. The R value for these specific units for millimeters of mercury is going to be 62.36. And that R value does change depending on your units for your volume. So make sure you're paying attention to your volume units. And then we're going to multiply that by the temperature, which we have as 298. This calculates out to 1.58 times 10 to the negative third moles. Now that we have moles, we can just do a molar mass calculation, which is just moles divided by mass. Our mass is in milligrams. We're going to want that in grams. So again, there's 1,000 milligrams in 1 gram. So we have to move the decimal place 3 times. So that's actually 0.095 grams. So we'll take our mass, which is 0.095, and divide that by our moles, which is 1.58 times 10 to the negative third. Gives us a molar mass of 60 grams per mole, which is twice as much as our empirical molar mass. So since we know that the actual molar mass is twice as much as the empirical molar mass, what we have to do in the formula is multiply everything by 2. So our actual molecular formula would be N2C2, and we had 4 hydrogens before, so it's actually going to be 8 hydrogens. So we're doubling the amount of everything from the empirical formula, and we end up with this molecular formula.